In this third video on designing an abstract function from two or more examples of highly repetitive code, we're going to work on the signatures of the abstract functions. The signatures come last because with abstract functions, they can sometimes be the hardest thing to do. In order to learn how to write these signatures, we're first going to have to learn a couple more pieces of notation that we can use in type comments and signatures for describing them. So here we go. I'm in parameterization v3.racket. And what I need to do now is finish up the signature for the abstract function contains. Remember, we're abstracting a function from two or more examples of highly repetitive code. I can't say that 3 times fast. And doing that requires us to work backwards through the HTTF recipe. So it's time to do the signature. And the way I'm going to do the signature here is a little bit different than the way we've done it before. What I'm going to do is I'm going to look at the code and read the signature off of it. Some programming languages do a thing like this automatically, and it's called type inference. So here's how it's going to work. The first thing I do is I look at the function and I see that, let's see, there's 2 arguments. And of course, every function always produces one result. So there's an arrow. What do I know about these 2 arguments? What I'll do is I'll put a placeholder there to remind me that there's 2 of them. And what do I know about these 3 positions? What can I write here? Well, when we do this kind of type inference, we look at the function and we start with the sort of most clear thing we can find, the most unambiguous information about the type of something we can find. And when I look at this function, I see that in its base case it produces false, and here it produces true. So it's immediately clear to me what type of value this function produces. It produces a Boolean. So I can just put Boolean there. I read that because, remember, there's a false there and a true there. This function is producing false and true. It's therefore producing Boolean. Okay, let's keep going. Let's look at this first parameter, s. What happens to it? Well, let's see. Here s is passed in the recursion, so that doesn't really tell me anything particularly about its type. But look here. Here s is passed as an argument to string equals. And string equals needs both of its arguments to be a string. Therefore s has to be a string. So I know that the type of the first argument to contains question mark is string. Again, let me say how I discovered that. I see that the first argument to contains s is used as an argument to string equals. I know that string equals requires both of its arguments to be strings, therefore s has to be a string. So I could put string up here as the type of the first argument to contains. That just leaves me with this argument. Let's see what happens with that argument. Well, here I take first and rest of it. So I know it's a list. And I'm going to give you a new present here that we can use in terms of writing types, which is instead of defining list types and writing list types the way we've always written them, I'm going to let you just write list of and then something here. And that's going to mean a list of that. Let me keep going and I'll come back to this list of thing. If I look here in more detail, when I take first of the list ends up being an argument to string equals. That means first of the list has to be a string because string equals wants its arguments to all be strings. So this here, this first and rest told me that LOS had to be a list. And the fact that this first of LOS is used as an argument to string equals tells me that it has to be a list of string. So I can write this like that. And again, just to explain this list of string notation, what you're allowed to do from now on in the course is anytime you want to have a list of type, list of string, list of Boolean, list of drop, list of whatever you want to make it be, instead of having to define the whole type the way we've been doing with full-on data definition, something like this, from now on you don't have to have the data definition. You can just write open paren list of and then the type of the elements of the list and a closed paren. So that's a little present here in the middle of how we produce the signature of abstract functions. So there's the signature of contains. Let's go on and do the signature of map2. It's going to work the same way. Let's see, map2 clearly consumes two arguments, and it produces a result. What do I know about those arguments? Well, let's see. This first argument, fun, is a function, because right here I'm using it as a function name. So fun better be a function. So how are we going to write the type of a function when it appears in the signature of a higher order function? Well, the way we're going to do it is like this. We're going to put an open paren, and then we're just going to use a paren to wrap itself. We're just going to use parentheses to wrap themselves around the signature of the function. So this part here will be the signature of fun, because it's the type of the first argument to map2. This will be the type of the second argument to map2, and after the arrow will be what map2 produces. Okay, what else can we tell from here easily? Well, in the base case, this function produces empty, and in the non-base case, it produces cons of something and the natural recursion. So this function is clearly producing a list. So we can write list of there. Well, what do we know about the elements of the list? What can we find out about this parameter? Well, here we see that this function is taking the first and the rest of its second argument, lon. So that means this thing is a list too. Notice I'm gradually building up more and more knowledge about the signature of the complete function. Now I want to stress here, there's no single right order to go through these. Okay? I kind of tend to go from the easiest pieces of information I can pick up about the type to the ones that require more work. There's different orders you could go through this. What matters is that you end up with the right signature for the abstract function. Okay, so what do I know about the elements of this list, the list which is passed to map2? Well, to figure that out, I should look for a place that calls first on the list. And the only place that calls first on the list is right here. And notice something very interesting, which is that first is passed immediately to the function argument to map2. So map2 itself never sees the first of the list. It doesn't really know what it's going to be at all. What it does know, though, is that whatever type of thing first is, whatever the type of the elements of the list is the same type that function better be able to accept. So we've got an interesting thing. The elements of the list, as far as map2 is concerned, can be anything, but they have to be something that function is prepared to accept. And so I'm going to introduce a new notation that allows us to express that. And what we're going to do is we're going to say, well, the type of the elements of this list can be anything. So we're going to use what's called a type parameter. And by convention, type parameters are uppercase single letters of the alphabet. So here we're saying, the list can be of any type, call it X, but fun has to be prepared to consume that same type X. So what these two X's mean is they mean anything you want as long as they're the same. Now let's look at the type of the result list. Well, there we need to look at where the elements are put in the list, and that's with a cons. There's only one cons in here that builds up the result. And look at what it's doing. It's taking whatever the function produces and sticking it in the list. Map2 itself never really operates on what the function produces. It just sticks it in the list without looking at it. So that means that whatever function produces is going to be the type of the elements of the list. And we're going to use the same trick here. Is we're going to say, look, the function can produce whatever it wants. I'll call it y. But that's what map2 is putting in the result list, y. So let me read that from scratch. What it says is it says, hey, the signature of map2 is this. Give it a function that consumes x and produces y. Give it a list of x, and it will give you a list of y. So in the case of square, you've got a function from number to number, and a list of number, and you get back a list of number. But map2 can do other things. Why don't you right now assure yourself that map2 can do other things by doing this little problem where I just want you to write a check expect for map2 where the function argument you pass to map2 is string length. So write that check expect now.